Hello, everyone. This is Giacomo Beccari speaking, and I would like to welcome you all to the Hypatia Colloquium. Let me mute as well. To the Hypatia Colloquium 2022, to the new colloquium today. We have again two excellent speakers from our early career scientists who applied for this very challenging. There was very, very challenging, very we received a lot of applications. So we would like all the time congratulate to our speakers and invite all the other speakers to keep applying. We will certainly continue the series to help early career scientists to gain the visibility and to let us know about their science. And today we will listen to do again fantastic scientific results and science. Just let me give you some very quickly some technical details. So if you are watching the event on YouTube, you can use the chat to send the question to the speakers. Please do so by taking into account that there are roughly 20 seconds of delay between the time when you listen to the event and the time it is happening in live. So there might be a delay in giving you the answer, but it's still good if you can post it there, because then the speakers can look at it and answer even later. And for people who are attending the event on Zoom, please be aware that we are broadcasting on YouTube. So if you are uncomfortable with that, you can leave the event, please, and you can still follow the event on YouTube. And for them, basically, we will give each speaker as a half an hour slot, and then they can make questions. And the question session comes after the 20 to 25 minutes talk. And people from Zoom, they can raise their hand. The chair will give you the opportunity to raise your hand so you can make your question. The third way to make questions is also there is an online, in our Hypatia web pages, there is a form that you can fill and you can send your question to the speakers anonymously without then having an account that you should use, for example, on YouTube. With that, I would like to thank immediately Joanna and Murat. They are an ESO fellow and student. They are both working in Chile. So they are Chilean friends and colleagues, and I would like to thank them for helping us in chairing the sessions. As I would like to thank all our fellows and students that are constantly helping us in making this event possible. So thank you very much. And with this, I would like to leave the floor now to Joanna to open the session with the first speaker. Thank you very much.
Thank you very much, Giacomo. It is a pleasure to introduce our own PhD student, Avinash Chaturvedi, who is doing his PhD at the ESO headquarters in Garching as an IMPRES PhD student. So IMPRES is a PhD program between the Max Planck Institutes and the universities in Munich. And Avinash is going to talk to us today about understanding the mass assembly of the Fornax galaxy cluster. So please take it away, Avinash.
Thank you, Johanna. I will just share my screen. I hope that you can see my screen, and just confirm that you can see my mouse pointer as well. Yeah. Hi.
Yes, all fine.
Okay, thank you. So I will get started. Hi, everyone. Good afternoon. I'm Avinash Chaturvedi, and thank you, Johanna, for introducing me. And thank you to the organizers of Hypatia Colloquium for giving me this nice opportunity to talk about my research work. And today I'm going to talk about results mostly coming from my PhD research work, which is about understanding the mass assembly of Fornax galaxy cluster. At ESO, my supervisor is Michael Hilker, and I mostly collaborate with Glenn van der Ven, Nicola Napolitano, and Katja Farian. So let's get started with my talk, and briefly I will talk about galaxy clusters, and then I will talk about Fornax galaxy cluster. So galaxy clusters are the most massive gravitationally bound objects in the universe. And by studying them, we can learn about several properties. And here I'm showing you the beautiful image of the Fornax galaxy cluster. Usually, in the center of a galaxy cluster, we have most massive galaxies. Here, it's an early type of galaxy for Fornax, NGC 1399. We could learn about its structure, formation, dark matter content. On a lower mass regime, we have low mass galaxies, and these are the formation sites of the nuclear star clusters. And we could also learn how is the cluster environment is impacting the growth of galaxies, its formation and evolution. On a larger extent, we could learn how does the neighboring galaxies are interacting or merging with the central galaxy. For example, here in this plot, I show you the G-band image of central NGC 1399 galaxy, which you see here, and the image is here. And you could see its extended halo out to other neighboring galaxies, 1404, and for example, other galaxies as well. So these are some features we could learn by exploring the mass assembly of galaxy clusters in general. And usually, when we study one individual galaxy, then if we are going in outer skirts, like in the outer halo of galaxy, then using the integrated stellar light is quite challenging, because the star light goes fainter as we move in the outer skirts. So there we need some other kind of tracers to study the galaxy for its potential or other mass assembly kind of thing. And this is where global clusters comes in my study. So global clusters are the bright and compact sources, and they can act as a discrete kinematical tracers. And they are easily observable in the outer radii to few effective radii. For example, here I'm showing you the global clusters around one of the galaxy NGC 1379, which is one of the Fornax cluster member. And when we subtract the galaxy light from itself, we could see here the bright, here shown in the dark color, dots, which are the global cluster extending out to further few effective radii. And we could use these global clusters to study the potential or the gravitational potential of a galaxy itself. And I'm using global clusters of Fornax galaxy cluster, not to study only one individual galaxy, but this whole Fornax galaxy cluster. Till now, I have talked about two different scales. First, galaxy clusters, which is my case is Fornax galaxy cluster, and then the global clusters. And I'm using global clusters of Fornax galaxy cluster to study its dynamical mass modeling. But the question comes, why I'm interested in Fornax galaxy cluster? I will show you in a moment that why is very interesting. Fornax is one of the nearest and densest galaxy cluster. It has been observed quite well and has shown that it hosts a rich global cluster system. And some of the recent photometric studies have shown that there exist tidal and stellar streams between the central and other neighboring galaxies. Especially the last point makes this galaxy cluster quite interesting. And what I meant by this point is something like this. So there exist stellar and tidal streams between its galaxies. For example, here coming from the study of Iodish and al., who showed that there exists a faint stellar bridge between a central galaxy and one of the neighboring galaxy, NGC 1387. Some other studies have also found an overdensity of global cluster over this faint stellar bridge. This is the same thing in the G band, but showing here the contours are showing the overdensity region of global clusters. So, and most recently, using the Fornax Deep Survey, which is like observing the Fornax galaxy cluster in different photometric band, Cantiello et al. Produced one of the largest catalog of global clusters for the Fornax galaxy cluster. And they found an spatially extended distribution of global clusters in the Fornax galaxy cluster. Here in this plot, I'm showing you their selection criteria from the color plot G minus I, U minus R for selecting the global clusters. And I'm showing you this plot for the more restricted criteria to select the global clusters in this small contour. And if you make a phase space distribution of these global clusters, then we get a surface density map something like this, and you could clearly see that the spatial features is quite extended of global clusters in Fornax galaxy cluster. So these are some features which makes Fornax galaxy cluster quite interesting. So these things we know, that it hosts a large number of global clusters. There is a significant proof coming from photometric studies that it hosts intra-cluster global clusters, and also showing a quite active nature of cluster itself. But still we are missing something, like the mass assembly of this galaxy cluster. How is the mass assembly happening in this galaxy cluster? How is the individual galaxies being assembled? And what are these intra-cluster global clusters based on their properties, such as the kinematics or the color properties? And for exploring these questions, I'm performing the dynamical mass modeling of Fornax galaxy cluster to estimate its baryonic and dark matter disk profile. And from the science side, I'm very much interested in looking at the effect of what could be the role of intracluster objects in the mass modeling. And today I'm going to focus on the first part about the kinematics, and the dynamical part is my current ongoing project. And if you're interested in learning more about it, then I would be happy to talk. So let's focus about the kinematics of the global cluster. For measuring the kinematics, we need the global cluster spectrum. And in my case, the global cluster spectrum comes from the VMOS multi-object spectrograph at ESO VLT. And here you see the image of the VMOS spectrograph at the ESO VLT. And here in this plot, I show you the overall field of pointing coverage of our observations over the central 1 square degree of Fornax central region with this red square. This data set was already analyzed by Pote et al. In 2018, but they recovered a less number of global clusters from their analysis. So when I joined this project, there was a need to reanalyze this data set to recover a large number of global clusters. Basically, Pote et al., they faced some technical limitations, for example, in the ESO reflex pipeline of VMOS data reduction. So when I started this project, the first thing was to check whether the pipeline is working properly or not. And here I show you one of the example of global cluster for individual spectrum and the stacked spectrum in the black color in calcium triplet region of wavelength of the spectrum. And we noticed that the stacking of the VMOS of the spectrum from the VMOS reflex pipeline was working well. So this was the first thing to check, and then I modified the method or improved the method to measure the radial velocity. And for doing so, I used PPXF, which is a Python implemented tool to measure the radial velocities or also the higher order velocity moments based on the absorption features of the spectra. And here I'm showing you one of the model global cluster spectrum of a signal to noise ratio of 24 or 25, shown in the black color. And the red color shows the model PPXF spectrum. And the different blue bands are the regions which are masked out from the spectral fitting. On the right side, I show you the zoom in feature of different absorption features, H beta, H alpha, and also others. The important one is calcium triplet. We use these absorption features to select the final, use these absorption features and did the visual inspection to select the final bona fide sample of global clusters from our analysis. And before I show you how many global clusters we detected from our analysis, I would like to show you the plot of radial velocity of global clusters coming from the work of Pote et al. So here in this plot, you see the radial velocity map of global clusters within central 1 square degree. Here each dot represents global cluster, color coded with its line of sight velocity, whereas the green cross represents the major galaxies falling within this region of Fornax, and the central one is NGC 3099. So they found 387 global clusters, and after my analysis, this plot looks like this. So we were successful in almost doubling the global clusters on the same data set with improved analysis. And you could see that in the center, at least in the center, we produce almost homogeneous and uniform global clusters. So this was the first important result which we got after improving the analysis, that we doubled the global clusters on the same data set. And if I combine my data set with all other previous literature velocity map, then the radial velocity map looks like this. So after combining my catalog with other previously available radial velocity catalog, my work produced one of the most extensive radial velocity catalog. So here what I'm showing you is the full radial velocity map overplotted on a photometric surface density map coming from Cantiello et al. Study using the Fornax deep survey. And the global clusters, except mine, are coming mostly from Katia et al. And previously by Subert et al. So what you see here in this plot, in the background, in the gray and white, are the photometric surface density map. And the gray color, the white color, denotes the higher density of global clusters. And with my work, you could clearly see here that there are streams between these galaxies and here as well. And these are the photometric streams or intracluster global clusters coming from the photometric work. And with our sample, we are able to characterize these intracluster global clusters, giving a spectroscopic confirmation and also characterizing them with kinematics. So this was the second result. But we also were interested in seeing what kind of global clusters are tracing these regions. And for doing so, I needed to divide the sample in the red and blue global clusters. So global clusters comes in two subpopulations: the red, which are the metal rich, and the blue, which are metal poor. To divide the sample in these two subpopulations, I fitted a bivariate Gaussian in the color plot in G minus I and U minus R. Based on this separation, I divided the sample in the red global cluster, which is shown here in the top plot, and the blue global cluster shown in the bottom one. So here I'm showing you the line of sight velocity as a function projected distance, galactocentric distance from the central NGC 1399. And here the horizontal dashed line marks the systematic velocity of NGC 1399, which is the central galaxy of Fornax cluster. So you can notice that the red global clusters are mostly centrally concentrated, and they follow the systematic velocity of Fornax galaxy cluster, whereas the blue global cluster, they are spatially extended and they show a complex irregular kinematic pattern. Maybe it's not very easy to observe this feature. Also, I should remind that here the green cross represents the galaxies. The individual galaxies within the central 1 square degree. So maybe it's not very clear to follow what I said from here about the spatial distribution. So I tried to make a simpler plot like this, just making the phase space plot for global clusters color coded with whether they are blue or the red global cluster. So it's very clear from this plot that we see that the red global clusters are centrally concentrated on NGC 1399 and also on other individual galaxies, whereas the blue global cluster, they are more extended and they trace the intracluster regions. And if you notice carefully, then you could see that these streams or the intracluster regions are mainly dominated by the blue global cluster. I will tell you more about these intracluster regions in coming slides. So after this, not only on the phase space distribution, we also wanted to look at the natures of these intracluster global clusters based on kinematic and color properties. And for doing so, I wanted to get a clean sample of intracluster global cluster. But first, I wanted to match that whether our spectroscopic sample is correlating with the photometric sample or not. So for checking this, what I did, I selected the global clusters in the outer region, mainly in the intracluster region, and to be uniform, I made the selection in the rectangular boxes, and then I did the 2D case test between our kinematic sample and the photometric sample. And from the 2D case test, I found that our two samples are correlating. And then I tried to select the global clusters belonging to the individual galaxy to get a sample of intracluster global clusters. And for doing so, I made the selection for intracluster global clusters. So here it's a complicated plot, but I will try to explain it in a simple way. That here I'm trying to get a sample of intracluster global clusters. So here I'm showing you the global clusters around NGC 1399. So I selected all the global clusters within the two effective radii. I calculated its velocity scatter. And then at the time of this, any global cluster having 2 times more than this velocity scatter, I classified that global cluster as the intracluster global cluster. And here you see this kind of selection in this velocity space, first here in the phase space and then in the velocity space. And also all the global cluster which are outside two effective radii, I call them as the intracluster global clusters. Here they are shown in the black color, and the global cluster belonging to individual galaxy, they are shown in the red color. It's the same thing here in the velocity histogram. And the same thing for another example galaxy NGC 1374. So this was just a very rough selection for selecting intracluster global cluster, but it can be improved as well. So after removing all the global clusters belonging to individual galaxies, we will get a plot of radial velocity something like this. So here I'm just showing you the global clusters which are not bounded to the galaxies and classified as the intracluster global clusters. So you could see at the first notice we found that there are two streams A and C which were previously noticed by photometric studies, and you could see that they are in some kind of stream, and we wanted to look at their kinematic and color properties to comment on their origin. And also we noticed a higher density of global clusters in this region, F and G. So I followed the same naming convention as given in the literature. So I called them A, C, F, G. And then I tried to look at their kinematical properties and color plot. So just to remember that which stream we are looking here, I tried to plot it here as well, just we can connect. So if we in this plot, what I'm showing for the top panel shows the radial velocity, and the lower panel shows the color histogram for the global clusters falling within these selected contours. So in stream A, we notice this is this one. We notice, and also here the black curve shows the histogram of total global cluster, whereas the red histogram denotes the red global cluster within these streams. So we found that the stream A has two velocity peaks, which suggests that the global cluster in this stream is following the two velocities of cluster itself, and also coming from the neighboring galaxy NGC 1387. Whereas from stream C, we also notice two velocity peaks, and this suggests that the global clusters are coming from this galaxy, which is here NGC 1380, and also some accreted one. Whereas for stream F and G, we don't see here in stream F and G, we don't have any galaxy, and all the global cluster follow the systematic velocity of cluster, which is shown here as the dashed vertical line, black vertical line, and the yellow line marks the peak velocity, central velocity of the Gaussian. In the color plot, the interesting part is that in stream A, the global clusters are dominated by the red global cluster, and this clearly suggests that in stream A, the most of the global clusters are generated from potential stripping of 1387A by the central galaxy, whereas in stream C, F, G, we notice that most of the global clusters are blue global clusters, which are the metal poor global clusters. So this suggests like these are maybe the remnants of the low luminosity galaxies destroyed by the infall or the accretion, especially for the stream F and G. And then after this, I would like to show you just one last plot, which is about my dynamical modeling about the velocity dispersion plot profile of the global clusters. So here I'm showing you the velocity dispersion profile as a function of the galactocentric distance. Here, the red and blue dots denotes the velocity dispersion of red and blue global cluster, whereas the black curve or the gray curve denotes the total velocity dispersion profile. And we noticed that around 10 arc minute or 58 kiloparsec, the total velocity dispersion profile flattens, and this suggests that from this point onwards is the cluster potential which is dominating. Although it's not very clearly visible in this one, because it's dominated by the global clusters belonging to these individual galaxies, and you see the fluctuations marked at these positions. But this feature is visible in the intracluster global cluster velocity dispersion profile, that it almost flattens. And right now I'm using discrete chemodynamical modeling, which is based on MCMC approach, to estimate the total mass estimate and also looking at the dark matter halo properties. Finally, I would like to advertise one thing that we recently got Fornax cluster VLT spectroscopic survey data using flames and force 2 observations, a spectrograph. And here I'm showing you the different pointings. This observations are mainly based to understand the nature of intracluster global clusters. And currently 70% observations are done, and in the next round more will be all will be done, and this will be important to derive and to understand the metallicity of intracluster global clusters. And finally, I would like to conclude my talk with this point, that our work led to produce one of the most extensive radial velocity catalog of global clusters. We found that the metal poor blue global clusters dominate the Fornax cluster intracluster regions. Our work led to identify and kinematically characterize the Fornax substructures. As a first hint of dynamical modeling, we noticed that the velocity dispersion profile flattens around 58 after 58 kiloparsec. And for more details, you can check my paper, and this catalog is publicly available. So I hope it will be helpful, and that's all. Thank you.
Thank you very much, Avinash. This was a super interesting talk, and also thank you for sticking to the time. We have some virtual applause. So let's give the people in the audience a little bit of time to think about questions. Maybe if there's not a... Oh, Giacomo, do you have a question, or do you see a question?
I do have a question, actually, if possible. Sorry, can I, Joanna?
Yeah, sure.
Yeah, thanks. Thank you, Avinash. It's a beautiful data set, and the complexity is, is big. I think I wanted to ask you, this is, it's not my field, so sorry if the question is not relevant or something. So in the slide, I think it was 26, probably, where you show the radial density, the radial distribution, velocity dispersion profile, exactly. So these are the blue and red galaxy global clusters, right? And the same have also, they do show a different density, radial distribution with respect to the center of the cluster, the Fornax cluster. So I was wondering, did you expect such a velocity dispersion profile, given the different, the different radial distribution, you see what I mean? What does it tell you about it? So the fact that they are distributed radially. So what I was expecting is a more...
So basically, let me try to explain this plot, and maybe it will. I was unable to understand your question, but maybe you wanted me to explain that what do we understand from this, maybe. So red global clusters, you could see that they follow a less velocity basically the velocity dispersion profile gives you a hint about the kinematic energy, how stable or how random is the velocity dispersion,
Yes.
velocity motion basically. And we see that the red global clusters, they have lower velocity dispersion, so it shows that they have a quite similar velocity, whereas for the blue global clusters we see a higher velocity dispersion, so they are widely scattered and they are quite random.
No, exactly. But the fact that very good. Exactly. This is exactly. But the thing that, in fact, the fact that the second point in the blue, so the first point is so, at least so close to the red one, and then the second one goes up. So
okay. Yeah.
This is expected. Kinematically, is something. Or you were expecting a more solid difference.
So actually, here each dot represents 50 global clusters. Okay, and I noticed that even if I make a small binning, I could see that the velocity was increasing. But I wanted to cover them in the outer regions and to be more homogeneous. To see this behavior clearly, I use this kind of binning scheme. But I tried to look at the maybe this if we come here, basically if you make the bin here and here, then you would see that still the velocity is quite spread in this region. So they will
yeah. No, because I found interesting that it goes, so I don't know, that it's identical and then it goes up, some parsec after the center, basically.
Yeah.
like something is warming up. I mean, it's cooling down. I see it's slowing down basically.
So this thing is coming, like it's a significance that it's maybe coming from this neighboring galaxy NGC 1404, and this is what we see basically here. That till NGC 1404, the global clusters are mixing up, and that's why around this point onwards we see that the blue global cluster have higher velocity dispersion. Yeah.
Okay, it's very. It's a lot of.
I would like to use my chair's privilege to add that to your question, Giacomo, that from cosmological simulations, if you look at tracer particles tracing the galaxies or tracing the intracluster light, you indeed expect such a behavior that you have a higher velocity dispersion. And since Avinash beautifully showed how his blue globular clusters predominantly trace the ICL, I think it's very nice to see this here in observation. Do we have time for a second question from the Zoom?
I see Dietrich has raised hand.
So please, Dietrich, go ahead.
Yeah, thank you. Very nice talk, Avinash. The fact that all the clusters which are in the intercluster medium are blue, does it mean that these were clusters which were formed rather far away from the initial host galaxies and therefore could be stripped off more easily? Whereas the red clusters are closer to the host galaxies and are more firmly bound gravitationally?
Yes, exactly. This is what I wanted to show from this plot, especially from, yes, so to answer your question, yes, I believe that the blue global clusters are the remnants, or they are the remnants from the destroyed low mass galaxies. And this is what we see in stream F and G, where we don't see any particular individual galaxy, and we see mostly predominantly the blue global cluster. So this is kind of hint previously also showed in previous studies that the low mass galaxies host larger fraction of blue global cluster. So this signifies that these are the remnants of the low luminous galaxies.
Okay, thank you.
Yeah. Thank you.
If there are no further questions, let's thank Avinash again. And I would hand over to Murat to introduce our next speaker.
I will stop sharing. Thank you, Johanna.
Hello. Our next speaker is Paulina Sowicka, and she's a PhD student at Nicolaus Copernicus University in Warsaw, in Poland. And today she's going to talk about pulsating white dwarfs, specifically concentrating on GW Virginis instability strip based on the observations of PG 1159 stars. So Paulina, you can start once you're ready. Paulina, you are probably muted. Yeah, we can see your screen, but we cannot hear you at the moment. Yeah, at the moment we are facing technical problem, I think.
Yeah, Murat, maybe we made the test before, but it was I see. So from what I can see, maybe Paulina, so the audio is on, but the video is
Hello?
not. Now I can hear you.
Oh, okay. I don't know what happened.
You can start sharing your screen, Paulina.
Yeah. Okay, so once again, can you see it now and hear me all good?
Yes, yes, we can see your screen and we can hear you well.
Perfect. So again, thanks a lot for the introduction, and thank you to the organizers for this opportunity that I can share a little bit of my work with you and tell you about my observational work on my favorite stars, which are PG 1159 stars. So let's go ahead and get started. Pulsating stars come in different flavors, as you can see in this theoretical HR diagram. They are located all over the place. And I'm mostly interested in the ones that reside along the white dwarf cooling track, which is marked here in this shaded area. And also in this region, the white dwarfs form different groups, but there are three classical ones. The first ones are the hydrogen deficient white dwarfs, the GW Virginis stars that are located around here. Then we have the hydrogen-rich DAVs and helium-rich DBVs along the cooling track. The GW Virginis stars are the ones that I'm the most interested in. And as you can see, they span a wide range of effective temperatures and surface gravities. So this is there are many different configurations of these stars. And here you have the close-up of this area. That again, there are these different groups of white dwarfs, pulsating white dwarfs. The GW Virginis stars are distinguished mostly by their spectra, which are mainly of PG 1159 type, but there are also some of central stars of planetary nebulae of Wolf-Rayet type. And these stars have carbon, oxygen, and helium-rich surface abundances. Here you can see the typical values, but actually we can see a strong variation of the ratio of these elements from star to star. So we have really many different configurations, adding to that also the effective temperatures and surface gravities. They are really unique stars. And the main spectral feature that these stars are distinguished by is this absorption trough that you can see here in three examples of different stars with different effective temperatures. And this is made by the helium-2 line with adjacent carbon lines. So this is the main spectral feature. We see that, and we can say it's a PG 1159 star. Some of these stars show photometrically detectable low amplitude pulsations, multi-periodic, that have periods of the order of several minutes. And here in this plot, you can see a light curve of PG 1159 star compared to the light curves of other pulsating white dwarfs. These pulsations are due to the non-radial gravity modes driven by the kappa mechanism associated with the partial ionization of K-shell electrons of carbon and oxygen in the envelopes. And also there was a theoretically predicted additional mechanism called the epsilon mechanism that is associated with the changing nuclear energy generation rate in the helium burning, in the stars with helium burning shells. And actually we have this new instability strip where we have the paths where both of these mechanisms theoretically can operate in a star. And as you can see, there is it's this shaded area, and there is a number of stars that reside in this region, although so far it hasn't been proven observationally that this additional epsilon mechanism operates in any kind of a star. And these stars are thought to be formed as a result of a born again episode, which is either a very late thermal pulse that is experienced by a white dwarf that is already on the cooling track. It's this solid line in here, so it departs on this part of the evolutionary track. Or a late thermal pulse that occurs during the post-AGB evolution when hydrogen burning is still active. So it's this dashed line that it happens in this part. And the presence of hydrogen, there is a group of stars that is called hybrid PGLM59s. Together with this nitrogen, are trace elements of this evolutionary history. So by seeing whether we have hydrogen and nitrogen, we can say when the progenitor experienced this final thermal pulse. But actually the most striking characteristic of the GW Virginis instability strip is that it is not pure. On the contrary to the DBVs and the DBAs, we see only about 50% of the stars that are within the borders of this instability strip to pulsate. And that has very important conclusion, because it means that the variable and non-variable stars populate similar effective temperatures and surface gravities. And it implies that the interiors that are studied with the methods of astroseismology are not necessarily represent the interiors of all the stars that are within this instability strip. And this is a very important consequence of that. And actually it raises a question of what separates the pulsators from non-pulsators, and whether there are some fundamental differences in their interior structures and those evolutionary histories. So the existence of these both pulsating and non-pulsating stars within the GW Virginis instability strip was a real challenge to pulsational theory. First of all, there was observed a nitrogen dichotomy, where it was found that all nitrogen-rich stars are pulsators, but all nitrogen-poor stars are all non-pulsators. So the natural conclusion was that the nitrogen is responsible for pulsational driving. Later, it was found that it's not the nitrogen, but it's actually helium enrichment, and that is enough, like too much helium is enough to prevent the driving of pulsations. So it's not that these stars had nitrogen, but they had too much helium. Later calculations showed that actually the high abundance of oxygen is responsible for pulsational driving. And finally, there were two stars studied with the same oxygen and carbon abundance, but different nitrogen abundance. So one was nitrogen rich and the other one was nitrogen poor. And it turned out that the pulsator is nitrogen rich and non-pulsator is nitrogen poor. So that came back to this first idea that it's the nitrogen that is the driving mechanism. And the part that is played by nitrogen as a tracer of the previous evolutionary history of these stars is really interesting in this case, because we can ask a question whether it's the VLTP that is the mean that causes the nitrogen abundance to show up. Is it a necessity for destabilizing a star to have a composition required for a star to develop pulsations? And this would really allow this important conclusion that these GW Virginis stars have a fundamentally different evolutionary history to the non-pulsators. However, in this picture, there was still one culprit. And it was this star, P1154 plus 005. It's ever since the detection of strong nitrogen emission lines in its spectrum and the realization that all P1159 stars are pulsating P1159 stars are nitrogen-rich, a few years later, it was the only nitrogen-rich star that was never shown to pulsate. So it was an important one. A number of observers tried to detect these pulsations over the last 30 years. The first pioneering work by Grauer and collaborators didn't really show any variability on rather short time scales between 60 seconds and 1 to 2 hours. And this was a pioneering work, search for extremely hot pulsating stars. And regrettably, with this big survey, they didn't provide any information on the detection limits, didn't show any light curve, nothing to really show the other observers to follow where to look for these pulsations. And later on, over a decade later, Schuch and collaborators observed it twice and also did not detect any variability, and unfortunately also did not report any detection limits of these observations. Finally, Steininger and collaborators observed this star for 4 nights on a 1 meter class telescope and also did not detect any variability. But what is important to note in here is that the highest noise peaks here are on the order of 4 millimag. So this is for future reference, the detection of the noise floor for this star, for these observations. And we included this star in our survey for variability among PGM59 stars that we've been carrying out for a couple of years to kind of come back to those stars that had null detections or that their variability was never checked. And we observed it with the GTC on La Palma 10 meter class telescope, so quite a difference between 1 meter and 10 meter class. And with this short, only about an hour long observations, we were able to detect variability in this star. The time scale, the time duration of the observations was really short, so we couldn't really say much about the nature of pulsations, only to kind of see where the peaks might be, but that's basically all that we could say. And of course, this is a good evidence that this star might be pulsating and therefore might belong to the GW Virginis family. And it of course called for confirmation, also because these periods were rather long, so 1 hour long light curve is not really enough. And actually a few observing runs later, we finally managed to get the confirmation in May last year using 1 meter class telescope in South Africa. And we observed it for 5 nights. And as you can see on this nightly Fourier spectra, there are some pulsations. And what is really characteristic of these stars is that the frequency spectra change even nightly. So from one night to the other, you can see that the amplitudes of the peaks vary. The frequencies in this case mostly stay the same, but the amplitudes really vary. So you can see that, for example, in here, the amplitude reaches about 6 millimax, while in the other nights, it's like about 4 millimag of the same peak. So there is really a difference. And here I come back to these previous observations of Steininger. Their highest noise peaks were at 4 millimax. So here, the mostly on most nights, this one peak is about 4 or 5 millimax. So if these pulsations were there, they were just hidden in the noise of these previous observations. So that also shows that these stars are really difficult to observe because these amplitudes are really, really low. So here we are coming from this nightly Fourier spectra to the combined spectrum from these all nights. And we can see a few groups of peaks where we detected pulsations around 40, 55, 90, and 110 frequent cycles per day. And this there is, however, one thing to note, that actually these higher frequency groups might be combinations of the lower frequency groups. So we with the data at hand, we cannot say that these are all independent frequency modes. And here you can see that our frequency solution and frequencies, amplitudes, and phases were determined by simultaneously fitting a nonlinear least squared solution to the data. And this is the formal solution. We omitted the frequencies below 10 cycles per day, where all of this stuff. And compared to the periods that I put in here in red of these frequencies on the diagram with observed and theoretical period ranges of other GW Virginis stars. And as you can see, it fits within this range. So we can say that this is consistent with the pulsations driven by the kappa mechanism. We also looked for the epsilon-driven modes, which are higher frequency modes in this nightly spectra. I'll show it again. But as you can see, that in these regions, it's nothing in there. So it's another non-detection of these epsilon-driven modes. So we obtained new observations of nitrogen-rich PGLM59 star that allowed us to discover the long sought-after pulsations in this star. The first run from the GTC showed us that this star might be pulsating and gave us a hint of the amplitude ranges and the frequency ranges that we should look at. And our follow-up observations over 5 nights showed clearly that these are low amplitude multiperiodic pulsations in this star. So for the time being, there is a clear separation that all nitrogen-rich PGLM59 stars pulsate, while the others do not. This is evidence that pulsating and non-pulsating PGLM59 stars have different evolutionary histories, and it seems necessary that the star undergoes a very late thermal pulse to become a pulsator, while nitrogen is a tracer of this history. So is the nitrogen problem to solved and the whole picture is complete, or will we be able to find more nitrogen-rich non-pulsators and nitrogen-full pulsators if we push the detection limit down? So even though this evolutionary link appears to hold, it's really statistically a really small number, because only 14 stars of these almost 60 known PGLM59 stars have nitrogen abundance or any kind of limits on it assessed. So we need more observations, and we are doing that. We both need spectroscopic observations with high signal-to-noise ratio, because this nitrogen abundance, even in the nitrogen-rich ones, is very low. And also we need more photometric observations to check these non-pulsators, whether these are really still non-pulsators. And it is really worth reobserving these known non-pulsating stars and pushing this detection threshold down, as was shown in here. It really gives results. So this is a preliminary plot with a portion of stars that we observed in the survey, and there is one non-pulsator, which was just as a check for the method. There is the PG1144 from the GTC, and there is also another suspected pulsator that still needs confirmation. So this is still work in progress, and we are hoping to finish this work soon. And with that, I'll go to sum up. We discovered pulsations in PGM44, the only known nitrogen-rich star that was never shown to pulsate. And that confirms the link between the nitrogen abundance and pulsations for the time being and for the number of stars that we have studied. We will continue our survey for variability among non-pulsating PGLM59 stars. And we also carry out spectroscopic observations of these stars to derive the abundances, mostly focusing on deriving the nitrogen abundance. And our goal is to have a well-studied sample of this group of stars with the full information of their evolutionary history and whether or not they pulsate. And with that, I'd like to thank you for your attention.
Thank you very much, Paulina, for your nice talk. And questions? So I have a question.
Mm-hmm.
So for many targets from your list, probably will be observed with space missions such as TESS,
yeah,
or during K2 mission. Do you expect to find more pulsating stars, or these observations going to help for your research?
So I hoped for TESS, and I would say that personally, I'm a bit disappointed with the outcome because, for example, PG1144 was observed recently with TESS, and it seemed like a perfect target because it's isolated and it's not that, it's quite bright. And to like my disappointment, there was only one peak. And it was a different peak than the ones that we detected from the ground. So there is really not much that we can do at the moment to move forward with this star to study it astroseismically. So this would include really, ideally for these stars, we would need a different mission, space mission, and yeah, just something for the future, because observing it from one side is really challenging, where you have so many daily aliases, and weather is can be tricky. So I really hoped for TESS, and for some stars it proved that it's really it really worked well. But for the ones that are not checked for variability, it's not enough because they are too dim mostly. Mostly they are from the SDSS survey. So it's like 17th magnitude, and observing a blue star that faint with a red band telescope, it's not gonna work that well.
Yeah, you're right. And this seems quite dim for the TESS mission.
Yeah, that's why we went with this 10-meter class telescope with only 1 hour long observing blocks, but it's at least something to see if there's any kind of variability going on in this star, to have an idea and to move from that.
Yeah, thank you. So we have time for one more question, I think. So again, thank you very much for your talk, Paulina.
Thank you.
And there are a couple of questions. Sorry, maybe
I couldn't say. Yeah.
No, sorry. Maybe Dietrich, go ahead. Mine was a general one.
Yeah, Paulina, very nice talk.
Thank you.
Would there be any advantage in observing these stars in 2 or more passbands simultaneously?
So from what we know, not really. There are really no studies that would help us with these multibands for example, mode identification of these stars. So for now, we just focus on observing in one band to just gather as much light as we can to have these detection thresholds as low as possible for now.
I was not really thinking of the astroseismology and the mode identification, but just to have parallel observations, which should then have a similar pulsation spectrum, because you said the pulsation spectrum looks different every night.
Yeah.
Okay, thank you.
Okay, thank you again. And we can conclude now. We can close it now.
Yeah. Murat, thank you. Thank you very much for chairing the session, and thank you also for Joanna, and to our speakers, of course, Pauline and Avinash. Thank you very much for your talks and for your presentations, and good luck for the rest of the coming months and for your careers, of course. And I really wish we can see each other live very soon again. With that, I also would like to thank the participants for coming, and I guess we see you in a week from now for the next Hypatia series. Please be aware that all the talks are available online, and as CVs of our speakers, and soon we will have also the proceeding of this year series of events. With this, we can close. Thanks again to everyone, and see you next week. Bye-bye.
Thank you.
Thank you.
Thank you, Giacomo.